Okay, so I see there are already 4 students. My suggestion is to watch at the screen on YouTube and to use 4K resolution, so use enlarge the screen to the maximum, to enlarge the YouTube window to take all the screens so that you can see better in high resolution. Okay, I think we can start. Welcome everybody. Virtual welcome, because evidently you cannot be here with me. We will try to use this system to make remote teaching. I apologize, I know it's not perfect. I'm totally aware of that. I know it will be somehow difficult for you to make questions because there is some delay. There are about 12 seconds delay between the time here and the time the video is streamed on YouTube, but somehow we'll try to make it working. First information about the laboratory. As you know, we cannot have real laboratories here in the faculty because we should keep social distancing. Nevertheless, we are creating some sort of videos to let you experience, at least to some extent, what you would have experienced in the laboratory in real life. I will give you more updates about that next week. If you want to make questions, I think the best way to do it is to use Teams. So if you are registered for this lecture, for this course, you have automatically access to Teams to MS Teams of this course, and then if you are in Teams, you can simply connect to the streaming. You will see also my face directly here, but I suggest you to watch on YouTube for higher resolution, and you can directly unmute your microphone and talk and make a question there. I have my computer here, so I can listen you if you want to talk. That's the best way to do it. If you want, you can also turn your camera on so I can see that there is real people from the other side. It might help me to feel less alone. Okay, let's start with the first lecture. Then later, maybe I can give you some extra information about the course. The first lecture will be divided in 2, as all the lectures of this course. 1 lecture on Thursday and 1 lecture on Friday. The lecture number 1 is about sampling and quantization, AD converters, and digital scope. I hope you can see from the screen. If there is some problem, just let me know. Typically, when you want to make a measurement, you start from a sensor. It could be a sensor of pressure, a sensor of temperature, a sensor of force, whatever. You have a sensor which gives you an electrical quantity. It could be a resistance, a voltage, a current. Then what you do is to amplify this quantity if it's too small. For instance, if you have a thermocouple, you get a voltage which typically is very small. If you want a precise measurement, you need to amplify it. So you will have an amplifier which amplifies that. You have some signal conditioning, which means, for instance, that you want to change somehow this quantity. For instance, you have a sensor of temperature, which gives, as a response, a resistance, and you want to transform it into a voltage. So this is all under, or for instance, another example, you have a signal which contains a large DC value, and you want to decrease it and cut away the DC value, and then amplify it. This is all under this frame of amplification and conditioning. Then you convert this quantity into a digital signal and you process it. Why? Because we don't live anymore in the times when you have these old wooden boxes with some meters, with analog meters. Now all these measurements are digitized because you actually process them on computers. In this course, we will make everything belonging in this measurement chain. However, we will do it vice versa. So we will start from the processing with the digitalization, which is the last step, in fact, the last thing you do when you make some measurement. Then we will go to amplification and conditioning, and eventually in the second part of the course we will go into the sensors part, okay? So we will see several sensors used to measure several physical quantities. So now, today, let's talk about the digital world. Let's keep in this frame where we move from the analog world, where you have a voltage, and we go into the digital world where you have some numbers, okay? So the concept of this digitalization is in fact very simple. You have an analog voltage, for instance in this case a signal C, which has a value from 0 to 5 volts, and then you convert it in a digital code. That is a code going from 0 to 255 in this example. Could be to another number. But in any case, it will be a finite, an integer number. The first difference between an analog voltage and the digital code is that the amplitude is quantized. So if you have an analog voltage from 0 to 5 volts, you have any value between 0 and 5 volts, which can have, the voltage can have any value of the, between 0 and 5 volts. For instance, in this case, I picked 0.84 volts, but it could be 0.841, or 841 to 3, 4, 9, 7, whatever. It could be, there could be infinite numbers after the decimal point. Why? Because it's an analog voltage, so it's continuous. When you transform it into digital code, that doesn't apply anymore. In a digital world, you have integer numbers. So if this voltage corresponds to a code of 43, you don't have 43.1 or 0.5. You have only 43. The next available number is, guess what? 44. Okay? Between 43 and 44, there is nothing. That's the very basic concept of integer number, which should be well known. So, the conversion itself between analog voltage and digital code can be represented like a staircase. You have an analog voltage which is continuous, and in the output you have digital codes which jumps from one code to another like a staircase. It means that in this example, for instance, if you have 5 volts of range and then 8 bits digital code, each step corresponds to 19.6 millivolts. If you don't trust me, you can calculate it. Actually, later we will see how to do it. This is a problem because we are already introducing an approximation, or we are introducing a difference between the original signal and what we get digitally. The digital code that we get is different, intrinsically different from the analog input voltage. By digitizing it, we are introducing a difference. What we get is not equivalent, is not perfectly equivalent to the input. For instance, in this case, all the values of the voltage between 39.2 millivolts and 58.8 millivolts always give the code 0000010 in binary. Of course, I consider it obvious that these codes are binary. I assume that everybody of you already know binary numbers, okay? It's just a different way to represent integer numbers. So it means that you can have a voltage changing in the input and the code is always the same. So you see that already you are modifying your signal. The width of each step of the staircase is typically called least significant bit. Why that? Because if you watch at the code, it corresponds to, in this case, 0, 0, 0, 0, 0, 0, 0, 1, binary, okay? This is called least significant bit. And for the record, this is called most significant bit. This is the equivalent to the value of the first step of the staircase, but it's equivalent to the difference of each step. So if you take, for instance, the third step, and you calculate the difference between the value 58.8 and 39.2, it's still equivalent to 19.6 millivolts. Now, quite often, you will hear people saying, the LSB, the least significant bit, is the minimum voltage that we can discriminate. Or they can say, the LSB is the minimum change of voltage that we can observe, that our digitizer, we will see later, can see. And this is not true. I'm sorry, but I heard many people saying this thing. But as a matter of fact, this is a lie. It is not true that the LSB, in this case 19.6 millivolts, is the minimum change of voltage that you can see with your digitizer if the LSB of the digitizer is 19.6 millivolts. Why? Let's consider, so this is the analog voltage, this is our code. We said that this step is 39.2. This is for 58.8 millivolts. And it is totally true that if you have a voltage here, let's say 41 millivolts, and you have, let's say, 42 millivolts, of course it's not to scale, clearly, you cannot distinguish them, because in both cases they give you a code which is 1, 0 in binary. You have a voltage which changes. It can be 41 or 42 millivolts, but the code, the output code is the same. True. So you might say, well, yes, the difference between them is only 1 millivolt. 1 millivolt. The difference of voltage is 1 millivolts, 42 and 41, is lower than the LSB, which is 19.6 millivolts. Of course, you don't see it. True. Oh, this applies also if you have 45. If you have 45 millivolts and 41 millivolts, the difference in this case is 4 millivolts. And the gain is lower than the LSB. So in order to see something, in order to see a code changing, you need a change of voltage which is larger than the LSB, right? No. Well, just imagine, for instance, if you have a voltage which is still, in this example, let's say 38. Let's write it bigger. 38 millivolts and 42 millivolts. Okay? Again, the difference of the voltage will be 42 minus 38, 4 millivolts. But now the code is changing. For 38, I get 1, the code, and for 42, I get 1, 0, okay? So it's not always true that a change of voltage in the input which is lower than the LSB cannot be seen. In this case, it can be seen. And at this stage, you might have an interesting idea. I could use this property to virtually increase my resolution. Resolution, by the way, is how many bits you have in your converter, in your digitizer. This is the first assignment for this course. You have to find a method to increase the resolution in order to see small changes of voltage, even with such a large LSB. There is a trick. Of course, you don't have to invent anything. Oh, if you invent it yourself, I'm absolutely fine with that, and I'm absolutely happy about that. But there is a method you might find out, you might research, which allows you to do some trick. I will give you some help. You have to add something to your system in such a way that you can see changes of voltage always. You can see changes of voltage lower than the LSB always, not only if by accident your change of voltage is right here at the edge of a staircase, okay, at the edge of one step of the staircase. Okay? In this case, you could see a change of voltage of 4 millivolts. In the previous case, you couldn't. You want to be able to see this change of voltage always. Okay? Fine. So this is the first assignment. For next week, I expect from everybody of you to tell me how to modify the system in such a way that always I could say a change of 4 millivolts regardless where the voltage is, okay? And I will give you one extra point for that. We will talk about the points later, of course. But it's the total course will give 100 points. So if you make correctly this assignment, I will give you 1 extra point. And okay, let's be generous. We are doing a pandemic, so we will make something better. We'll make 2 points. Nothing more, nothing less. Fine. So, if you go to some website where you find analog to digital converters, which are the devices which in practice they do actually perform this conversion, you will find, for instance, here you see, I was talking about the resolution. What does 8-bit mean? 8-bit means that the code, the digital code getting out of the analog to digital converter is represented with 8 bits. 8 bits in binary numbers. So it means that the code goes from 0000 to 0000 to 1111, 1111. Which means that in decimal it goes from 0 to 255. 255 because it's 2 to the power of 8 minus 1. If you have a 12 bits, clearly it goes from 0000, 0000, 0000, 0000 to 1111, 1111, 1111, which means from 0 to 4095. This is only the code. If you want to know the voltage corresponding to these codes, you must consider the reference. The reference is the maximum voltage you can give, which corresponds to the analog input range of the analog to digital converter. So sometimes the reference is internal. In some cases, for instance, there is a reference inside. In this case, it's 4.096 volts. Sometimes it's 2.5 volts, sometimes it's 1 volt. And it's already inside. You don't have to do anything. In some other cases, you have to plug to the analog to digital converter a voltage which becomes your reference. They give you typically the maximum and the minimum reference that can be used, and all the codes that you get out are referred to that external reference that you decided, that you plug. Okay? So, if you want to find out the value of the LSB, of the least significant bit, what you have to do is to take the maximum full scale values. In this case, for instance, it was 4.096 volts, and divided by the number of steps, okay? You take the full scale voltage and you divide it by 2 to the power of n. Why 2 to the power of n, where n is the number of bits? Because in a staircase, you have 2 to the power of n bits, okay? So you have 1, 2, in this case we have 3 bits ADC, 3-bit ADC, sorry, analog to digital converter. You will see this, acronym very often. So this stands for analog to digital. C is converter. Fine. For the record, this is just for an example. There is no 3-bit ADC. That would be terrible. Nobody would ever buy a 3-bit ADC. This is just for making a simple example. So don't go to the shop and say, I want a 3-bit ADC because my teacher said no, it doesn't exist, okay? Let's count how many steps there are. 1, 2, 3, 4, 5, 6, 7, 8. So in total you have 8 LSBs in this scale. So if you take the full scale, you divide it by 8, you get the value of the LSB. No, this is not true. Sometimes you see this on books, and partially it's also true, but that's not what happens typically. Why? Because if you observe carefully this characteristic, you will find out that it has an offset. Look at that. When we have a system, we typically want a characteristic between the input and the output, which crosses the 0, okay? Because in that case, the relation is straightforward. You just have a conversion between them, and you know that it's just enough to multiply the code, the output, the value of the output times a value times the slope, or 1 over the slope of this line, and you get the input. Fine. But this is not what happens in this case. If you watch carefully the staircase, you will find out that, in fact, it doesn't cross the 0. As you see here, if you approximate the staircase with a line, which is, let's say, the average of this staircase, you will find out that it crosses. This is the analog voltage. This is the digital code. It crosses the 0 here, not here. Which means that with the respect of an ideal input-output characteristic, you have an offset. This is called offset. The offset is a shift in the vertical axis of the characteristic. This is something that you do not want, okay? So how do we fix this problem? Next. Well, it's not that difficult. You can simply have half LSB wide step at the beginning and at the end. If you cut by half the first step of the staircase, then you find out that it will cross the line which approximates the staircase will cross in 0. But this means that the first and the last LSB should be half LSB. Now, if you count, you have half, 1, 2, 3, 4, 5, 6, plus another half. So in total, you have 7 LSB. So if your analog to digital converter uses this system, as it probably will do, you have to take the full scale voltage and divided by 2 to the power of n, where n is the number of bits, minus 1, in order to get the value of the LSB, okay? Now, we are engineers, or you're going to be engineers. So this difference makes sense if you have a, let's say, small number of bit LSB. If you have like a 24-bit 24-bit ADC, then it doesn't really change much. Just try to calculate 2 to the power of 24, even just to the power of 12, or to the power of 16, and subtract 1. It doesn't change that much. So if the number of bits is large enough, this difference almost doesn't bother you any at all. Now, how does the LSB affect the digital signal? We saw that by performing a conversion, we modify the signal. For instance, in this case, we have a 3-bit ADC, which still, I repeat, doesn't exist, with a maximum voltage of 2 volts. So the LSB, in this case, it's 0.25 volts, or less. It depends on which convention you use, on which structure of the ADC you use. And you see that you have this, this staircase, where you can clearly see in this graph that the red curve, which is the digital code we get out of the analog to digital converter, it's somehow following the input, but not precisely. There is some error. There is some difference between the blue line and the red line, and that is the quantization error that you introduce making this quantization, okay? If we take 4-bit ADC, you will see that this error is lower. If you follow the red and the blue line along the time, you see that the red line is always keeping a little bit closer to the blue line, which means that the error is lower. Probably you can see it better here because you see the comparison, okay? You see that at any point here, you might have the error, that is the difference between the quantization error, which means the difference between the red and the blue line, which is often larger than in the case for 4 bits. And then let's use 8 bits. Wow! If you use 8 bits, you cannot even see on the screen the difference. And you have to enlarge it to see the staircase. So the larger is the number of bits, the lower is the quantization error, and therefore the better is the representation of the representation given by the digital code of the input voltage. For the record, you might say now, wow, 8-bit ADC, it's cool. I love it so much. It's no. In reality, the 8-bit ADC is probably the lowest you can get on the market. I just used this to show that you increase the number of bits. For higher number of bits, it would be more difficult to show. But there are, of course, ADCs with much larger number of bits. Now, we have seen that when we make quantization, when we digitize a signal from analog to digital, we introduce an error, quantization error. So at this point, the question is, how many bits do I need? Because at the end of the day, we are engineers. So we have to design things. We should get some inputs for a project, and we should decide how we design our system to fulfill those requirements. And this is a very good question. But in order to get to the answer, we have to wait a little bit, because we need some extra information in order to answer this question. Be careful. This question is not trivial. There are many people out there which say misleading things about this topic, okay? It's slightly complicated, but if you follow me in the next hour, probably, you will see that we will arrive to the solution. Or maybe I could leave it as a surprise for the next lecture. So you will be at home tonight wondering, what is the answer, what is the answer, I cannot sleep, and tomorrow morning I will give you the answer, which is 42, of course. No, it's a joke. Okay, now, we have seen that digitizing our signal introduces a difference in amplitude. And but what about the time? We have quantization also in time. When you take a time-varying signal like this, like a sine, you have to necessarily take a finite number of samples. You cannot get infinite number of samples. It's impossible. In this case, we sample the signal here, then here, then here, and there is always a non-zero time between each sample and the following one. In this case, it's capital TS, which stands for sampling time. Now, in order to understand each other when we talk about these topics, let's use some definition, okay? So capital T is the period of the signal. In this case, we have a sine which has 100 Hertz frequency. So its period is 10 milliseconds. After 10 milliseconds, it will repeat again the same signal, okay? 1f is the frequency of the signal, in this case 100 Hertz, which is obviously 1 over 10 milliseconds. Then we have the n, lowercase n is the number of samples per period. In this case, 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh gosh, 10. So I made some mistake. Oh, it's not a mistake. Of course, this sample here at the end does not belong to this period. It will belong to the following period, just to be clear. If you have, I don't have chalk anymore. Here, if you have a periodic signal, like this, you take samples. Now I'm putting it randomly. Then you make 1, 2, 3, 4, 5, 6, which is not a good choice. Maybe I will have time to tell you why. But then this sample here belongs to the next period. In the very same way, this point here, this sample, belongs to the first period, okay? So this is the first period. And this will be the second period, okay? So be careful. The samples belonging to this period and always here. This belongs to the following period, okay? Then, capital TS is the time, the period of the signal divided by the number of samples, in this case, 10 milliseconds divided by 9, and the sampling frequency is 1 over the sampling time, okay? Fine. Now, the question is, I have this sine, 100 Hertz, and I sample it using 34 samples, so small lowercase n 34, or 9. And I ask you, which is better? Do you think, which is the set of samples which represents better the original signal? And here comes the problem of having distance learning or distance teaching, because you are here in front of me and you cannot answer. So I see somebody's connected, and with some delay, maybe somebody may answer me. So if you can see me online, you might unmute your microphone and vote what is better. I see, I cannot actually call your name in person, so legally speaking, maybe I have some message board here. Okay. So if you are afraid to say the answer, you can type it in the chat. Don't be shy. By the way, when I make questions during the lectures, I don't give grades for that, okay? So you are totally allowed to say something wrong. Well, of course, if you say something smart, it's better. But if you say something wrong, that's fine. I don't judge you. No answer? Come on, don't be shy. Well, really no answer? Oh, so sad. Most typically, people answer, well, 34, of course. There are more points, it's better. And well, typically 80% of the students reply that. And maybe some other students say, okay, okay, more is better. Okay, somebody suggesting, I cannot say that, maybe more is better, and also makes a smiley face in the chat. At least I have one person who was brave enough to say that. And then sometimes somebody says, okay, but that one is, sounds like a tricky question. Like, if it was so obvious, he wouldn't ask that, right? Yes, because as a matter of fact, 3 points are enough. If you know that you have a sine at 100 Hertz, and you want to digitize that sine at 100 Hertz, or for whatever you want, on another frequency, then, in fact, 3 points are enough. And this is typically the points when the student start losing hope, or they start not believing me anymore. Because that sounds weird. Just think about that. How the hell do you think you can represent this nice sine at 100 Hertz with 3 points? Again, you see 4 here just because this belongs to the next period. I mean, 3 points, seriously, that's terrible. I mean, let's say that I draw here 3 points. Now, in the chat, meanwhile, tell me if you feel uncomfortable about that, okay? Because students really feel uncomfortable in this situation. So, you have here, here, here. You have 3 points. Do you really see a sign here? I wouldn't see a sign at all. I don't think that any person in his good mind would see a sign here. If you plot it, of course, you can see it. But only with 3 points? No way. But that's it. That's true. Why? The key point was in the information I told you at the beginning. If you have a 100 Hertz sine, then it means that I'm giving you some information already. I know that I have 100 Hertz sine. And if I have 100 Hertz sine, what are the unknowns of this sine? How do you define a sine? Well, a sine S is equal to amplitude A times the sine of omega t plus a phase, and then you have a DC value, okay? Generally speaking, any sine can be represented by an amplitude, a phase, and then you have a DC value, because don't forget that you can have the phase, generally speaking, the amplitude, and then this can be shifted vertically, okay? So you can have an offset which moves up and down, a DC value which is added to the sine, and you should take it into consideration. So, how many unknowns do you have? A, the amplitude, phi, the phase, and k, the DC value. So, if you go back to your lectures of mathematics that you received at the kindergarten, you remember that if you have three unknowns, how many equations do you need? 3, of course. Well, you need 3 independent equations to be precise. But But that's what we have. I take the sign here at the beginning, okay? And I write the equation for the sign at time t1, which in this case is 0. So the sign, the signal at t1 is a sinus of omega t1 plus the phase and then plus the DC value. But this is just an equation, it's not enough. I will take the second one, which is S2, which corresponds to the sign at the time t2, which is equal to A, again the same amplitude, sine of omega t2 plus phi and then plus the DC value. And again for the time t3, okay? In this case, I have 3 equations, 3 unknowns. I can solve it, no problem whatsoever, okay? What if I have, okay, so at this stage, you should feel more comfortable with this idea. As you see now, if I have 3 points, those are enough. It shouldn't shock you anymore at this stage that 3 points are enough to define a sign. If you think about that, it's like, you know, when you were studying, somebody's writing something. So because, sorry. Yeah, exactly. So one of you is asking, so because we have 3 unknowns, then 3 samples are enough? Exactly. If you have to solve a system with 3 unknowns, you just need 3 equations. And where do you get those 3 equations? Simply by taking a point of the equation at 3 different points, okay? Probably you remember when you were at the elementary school that your teacher used to say, between 2 points, there is only 1 line, and you were comfortable with that. Of course, there are 2 points, there can be only a line. Well, in this case, the point is very large, so maybe you could make different lines. But generally speaking, jokes apart, it didn't shock you, right? There are 2 points, then there is a line, clearly. And for the sign, it's the same thing. For the sign, you have only 1 sign which goes through 3 points. Okay? If you have those 3 points, then there is only 1 sign which can cross those 3 points. Okay? And that's because you have 3 unknowns. Okay? So there is no other sign which fulfills those equations. Now, what if we have multiple harmonics? We don't have only 100 Hz, as we had before, but we have also twice the frequency. Here I have 1 omega t, and here I have 2 omega t. So the frequency is twice as large. So we have a first sign. In this case, I use cosine for reasons that it's difficult to explain. But you have amplitude 5, cosine of omega t plus 0 phase, which is the pink line here. And then I have a cosine at double the frequency, which is represented by this red line, which is a smaller amplitude, only 2, which is minus pi half phase, fine. And you see that it's twice the frequency because in 1 period it repeats twice. And then we have a DC value, which is 1. It's the green line. We sum them together and we get the bottom curve, which is the total of them. How many points should I take now? Now, if for 1 sign I need 3 points, for 2 signs we need, and typically people say, 6 points, because 1 sign, let's say, harmonic. I have 3 samples. Then I say, I have 2 harmonic, and everybody says 6 samples. No, unfortunately not. Again, what we have to do is to count the unknowns. What are the unknowns here? The amplitude of the first component, the first harmonic, 5, and its phase, 0. Then we have the amplitude of the second harmonic, 2, and the phase, which is minus pi half, and then 1, which is the DC value. So in total, you have 5 unknowns, and therefore you need 5 samples per period. Generally speaking, if I have capital N harmonics, I need 2 points for each harmonic. One for the amplitude, one for the phase. A1, phi1, A2, phi2, and so on, up to A capital N and phi capital N. So these are the points necessary because we have to find out for each harmonic the amplitude and the phase. And then we need 1 extra point for the DC value. So in total, we need 2 capital N points plus 1. If the signal has capital N harmonics, we need this kind of number, 2n plus 1, 2 capital N plus 1, okay? What does it mean? Okay, it means that the sampling period should be the total period of the signal, capital T, divided by the number of samples, which is 2 capital N plus 1. So the sampling frequency should be the reverse of the sampling time, which is 2n plus 1 divided by t, and then you find out that 1 over t, so the sampling frequency should be 1 over the sampling time, okay? But then you know that the sampling time is the total period divided by the number of samples, okay? So the sampling time is the total period divided by 2n plus 1, which is the number of samples, which means that you have 2n plus 1 divided by t, but then at this point you find out that 1 over t is the frequency of the signal, right? So it's equivalent to say 2n plus 1 times the frequency. So if the frequency of the signal is 100 Hertz and you have 5 harmonics, you will have, let me find another piece of chalk. You plug here 100 Hertz and here 5 harmonics, and you find out that you have 2 times 5 is 10, 11 times 100 Hertz, okay? This must be your sampling frequency. Fine. Now, let's be careful. This is the minimum frequency. The minimum frequency must be 2 times n plus 1, the main frequency. So, if you call Fn the maximum frequency of the signal, that is the frequency of the maximum harmonic, the frequency of the nth harmonic, okay? If you select a sampling frequency which is twice the maximum frequency of the signal, this is not enough, because this would give you 2n points in a period, okay? If you select only 2n, if you select twice the frequency of the maximum harmonic in the signal, okay? And you use that frequency as the sample frequency, in one period you will get only 2n, not 2n plus 1 samples. And you know that 2n points are not enough. You don't have equations enough to solve the system, okay? And I must stress this point because somewhere people might find this. I will erase this. Okay. Sometimes you will see in some book, actually I saw it, yes, also in some books, and even on some version of Wikipedia, that the sampling frequency must be larger or equal to twice the maximum frequency in the signal, okay? This is wrong. This is wrong because this says that you might have a sampling frequency equal to 2 times the maximum frequency of the signal, okay? This case is just one particular case of this. And this is not true. The sampling frequency must be strictly larger than twice the maximum frequency. Because this is not valid. And there was a student some time ago that it didn't trust me. Okay, does that mean that disregard the difference? Ooh. Does that mean that we disregard the different frequencies as unknowns because we arrive to a common sampling frequency? Wow, I don't understand your question. Let me just try to rewrite it somehow better because I don't actually understand your question. Meanwhile, I continue here. There was a student I was saying some time ago that didn't trust me because he saw some books where you could see this. And of course, he trusted more the book than myself. But this is a theorem. This is called sampling theorem. Or it could be like somebody calls Shannon theorem. Sorry, yeah. Somebody calls it Shannon, Nyquist, whatever. There are probably half a dozen of people that contributed to that. Nevertheless, this is a theorem. It means that it must be always valid. It's enough one single case to disprove it. And the simple case which disproves this is very, very simple. Let's assume to have a sine which has only one frequency. So n is 1. It has only one harmonic. Okay? One harmonic. So, if n is equal to 1, the number of samples per period should be 2n plus 1, right? Which means that is 3. 3 samples per period. That's what we saw at the beginning, when I saw that you have a sine and you need only 3 points for that sine. What if this theorem is true? Like, you will have something weird, because in this case, you would have 2 samples per period, right? You sample at twice the frequency of the signal. But what does mean sampling at twice the sampling of, or twice the frequency of the signal? It means that you start here, and then you sample exactly after half a period, if you have double the frequency, okay? Which means that the second point is here, at half of the period. And then after half a period again, and again after half a period. But then you end up with these points here that you see in the bottom curve, in the bottom graph. And you don't have the curve of the original signal anymore. Now, if you see this point, 0, 0, 0, 0, 0, 0, do you really think you can say which is the sign behind that? Well, no, you can't. And for a very simple reason. Because you have 3 unknowns, amplitude, phase, and DC value, right? But you have only 2 equations per period, because you took only 2 points per period. Which means that you might set, theoretically, 2 parameters, but 1 parameter will be always, you will be always unable to determine it. So you have infinite signs which fulfill, which cross with these points. And that's exactly what you have here. In this case, you can say that you have the DC value, which is 0, the phase is 0, and there are 2 parameters. But the third parameter could be whatever you want. It could be 1, 2, minus 1.5. Any value of the amplitude fulfills this equation, fulfills this system, sorry. you have infinite values, infinite sines with different value of amplitude, which cross those points. So clearly, 2 points per period are not enough. And therefore, this is not true. Okay? This is not true. Okay? Now, what happens if the sampling frequency is very, very low? Here I intentionally selected a sampling frequency which is way, way lower than the signal that we have to digitize it. I intentionally did this example to show you that sometimes you might see something which appears like a sign. In this case, you might see something. Oh. Okay, so the students say that never mind about that question, you made a mistake. Fine. So here you see something which appears like a sign, like a negative sign. And you say, if you watch only the red points and you don't see behind that the analog signal, because when you digitize it, at the end of the day, you watch only the points, you might say, okay, fine, I have a negative sign. Cool. I'm happy without that. But that's not the reality. The reality is the blue analog voltage, and you're measuring something totally different. You have what it's typically called aliasing, which means to see something else. To see something, believing is what you're measuring, but in reality, it's something else. Okay? So as soon as the sampling theorem is not fulfilled, you fall into aliasing. And in that case, you cannot say the data is less good, somehow approximated. No. If you are in aliasing, it means that you don't actually have any value from those data. You have more unknowns than equations. And you cannot say, yes, but I can approximate the system somehow. No, you cannot somehow solve, to some extent, a system which has more unknowns than equation, okay? So once you have less points than necessary, less points than prescribed by the sampling theorem, you can take your data set and throw it to the garbage can, because you can't do anything about that, with that, okay? Fine. Now, what happens if we take more points than necessary, okay? In this case, we had 2 harmonics. It means 5 points per period. But what if we get 13 points per period? Of course, you get more points than necessary, so it's useless. But what happens to the spectrum of the signal? First of all, what is the spectrum of the signal? You see here that we have our 5 unknowns: amplitude and phase, and DC value. Now, I said at the beginning that you, once you have the points enough to solve the system, you can theoretically solve the system. So you can go there, write this system of equation, and solve it manually. Like, good luck. Actually, there is a tool which helps you to solve this system of nonlinear equation, trigonometric equation. And that's the discrete Fourier transform. Of course, we cannot enter into details now of how it works, but trust me, it's a system which allows you to move from the samples taken in time into the value of the amplitude and phase for each harmonic plus the DC value. So once you perform the DFT, discrete Fourier transform, yes, which is the equivalent to the Fourier transform in continuous time. If you ever dealt with the Fourier transform, this is just the discrete counterpart. Okay. So in the input you have the sample in time, and in the output you have this spectrum. What is the spectrum? You have at each position of the harmonic the amplitude and the phase. For instance, at position 2 of the harmonic, you have the amplitude of the second harmonic. The second harmonic is the one which has 2 in front of the omega t, so it goes twice faster. Here the amplitude is 2, and here you see it's 1 here. What's the problem? The problem is that there are also negative frequencies, which again is a concept a little bit complicated to understand, but just take it as it is, okay? We unfortunately don't have real time to go into these details. If you want, you can multiply times 2, okay? Here you have the amplitude, and the phase is minus pi half. Here we go. Then you have the amplitude of the first harmonic, it's 5, divided by 2 is 2.5, and here you have 2.5. And the phase is 0. So here, in the spectrum of the phase, I will have 0. And then eventually we have the DC value, which has 1 amplitude, here is 1, and the phase is 0 because it's the DC value, so the phase clearly is 0. It's not a sign. So, once you take your 5 samples, you put it in the DFT, and you get to the spectrum, which gives amplitude and phase for each harmonic. Fine. Now, what happens if you have 13 points? Well, if you think about that, now we are using a number of samples which is larger. Which means that if you still write the equation, the number of samples, lowercase n, is twice capital N plus 1. In this case, it's 13, which means that capital N is 6, okay? 6 times 2 is 12, plus 1, 13. It means that now we can see harmonics up to the 6th order. And that's exactly what we see in the spectrum. If you take the samples, the 13 points that you get, and somehow I suggest you to actually do it. Try to simulate with MATLAB, with Octave, whatever is your favorite computational tool. Try to create these signals at home, just to be a little bit confident with that. And try to simulate this signal and compute the discrete Fourier transform. You will see that the output will give the amplitude for the first and second harmonic, and then just zeros for the third, fourth, fifth, and sixth. Why? Because there are no harmonics there. But if the signal had such harmonics, you would have space them to find. You would have space there in the spectrum for them. So having larger number of samples per period means that you have more space at the tail of the spectrum for additional harmonic at higher frequency, which is true. We increase the sampling frequency, so it means that we can accommodate harmonics at larger frequency. Somebody's asking, so the +1 represents the offset of the multiple harmonics. So I guess the +1, you mean the +1 in 2n plus 1. If so, yes. The +1, well, that's a little bit tricky question because let's put it this way. Theoretically, if you know that the DC offset, the DC value of the signal, is 0, and you know it for sure, you might have also 2n samples without the +1. Because you have only 2n harmonics. But that's not typically the case. That's why you need 2n plus 1 harmonic, 2n plus 1 samples. I don't know. Oh, by the way, if something is not clear and the question, we have some delay in talking. So if some question is a little bit, I'm not able to understand exactly what you're saying, just write me an email. We can, no, actually we cannot meet. So we can have some online consultation, okay? Fine. So this is the comparison. So again, if I have multiple number of samples, I simply have more points here that I didn't have before. Oh, by the way, when I say that I have a space, I have a value here at 1 for the first harmonic, and the value here for the second harmonic, I see that the spectrum exists only here and here. There is nothing in the middle. There is no 0, as somebody thinks. There is nothing, okay? Okay, so I actually understood the question and the answer was fine. So once you have your, once you have all these values from the DFT, you can in fact reconstruct the signal. Why? Because each point in the spectrum tells you the amplitude and the phase of each harmonic. So you can say, okay, I have a second harmonic with amplitude 2, which is 1 times 2, because you have the negative frequency. So amplitude of 2, phase minus pi half, fine, I draw a red line which corresponds to this amplitude and phase. Then I have a first harmonic with amplitude of 5 and phase 0. I draw the purple phase, the purple line. Then I have a DC value of 1, green line. I sum them together and I get the signal. Now, this is not actually how you do it, but there are better methods, mathematically speaking. But you can do it. You take your samples. So you take your signal and you convert, and you take the number of samples that, according to the sampling theorem, are necessary, 2n plus 1 per period. Fine. You perform the DFT, which means that you get the spectrum. The spectrum is here. It gives you amplitude and phase for each harmonic. Once you know the amplitude and phase of each harmonic, you can simply sum. You can create the cosine, the sines of each harmonic, putting there the amplitude and the phase for each harmonic, plus the DC value, and you get the signal. Now, there is quite a common misunderstanding in this case. When you reconstruct the signal in this way, you are not making an interpolation. Interpolation is when you try, either with straight lines or something with a more curve, to approximate the signal. In this case, you are not approximating the signal. Once you have this equation here, where you have all amplitudes and phase, and plus the DC value, for all the harmonics, then you are able to determine S of t for every single value of t. And you are able to determine S of t exactly, perfectly. This is not an approximation, which is obvious. We said at the beginning, how many points you need to know everything about the sign? 3. Once you have all those, if you have once you have those 3 points, you know everything about the sign. If you know that you can draw a sign because it has this amplitude and it has this phase, you know that you can write the signal as amplitude times sine omega t plus phi plus k. And for every value of t, you plug it here and you get the exact value of y. Okay? There is no approximation. This is very important because this is different from what we saw for the quantization in amplitude. With quantization in amplitude, you always have a quantization error. You cannot have an infinite number of bits in order to get a perfect representation of the signal, the digital signal corresponding to the analog voltage. You might have a very large number of bits, but if you watch close enough, you will always have some staircase which approximate the signal. And you will never be able to make this quantization error 0. There will always be some staircase, there will always be some difference between the value of the code and the actual signal that you are converting. Otherwise, you would need an LSB which corresponds to 0 volts. So 0 difference between the input analog voltage and the output code. Okay? So, for the analog quantization, you will always have a quantization error. But for the quantization in time, no. Once you fulfill the sampling theorem and you get points enough, you know that your representation is perfect. There's no mistake whatsoever. Okay? Fine. Now, let's watch better the spectrum. So here we have the first harmonic. which is, in this case, 100 Hertz, because we have a period which is 10 milliseconds. Then the last one will be capital N. In this case, if we get 13 samples, you have 6, so you have 6th harmonic, which means that we can multiply all these values times the harmonics, times the first harmonic. So here you will have 100 Hertz instead of 1, or 200 Hertz instead of the second harmonic, up to 600 Hertz, which corresponds to the 6th harmonic. Now, we have seen that when we increase the sampling frequency, you add tails, you add more points, more space available for higher harmonic at the tails of the spectrum. What happens if you increase the time you observe the signal? In this case, I call it acquiring time. You can get one period, 100 Hertz, 10 milliseconds, one period, and you get the spectrum. First, second harmonic, DC value. Everybody's happy. But what if you get 1, 2, 3, 4, 5 consecutive periods of the signal? In this case, again, you have more samples. So 2n plus 1 is larger. So you expect that you have new space on the spectrum, new space for new harmonic on the spectrum. But where? We don't find them, the new points here at the tails, but we find them between each harmonic. Why? Because now we move the frequency of our signal, which was 100 Hertz here, to a larger order of harmonic. We still have 100 Hertz. The signal is still 100 Hertz. Here, you see, it repeats equal to itself in 10 milliseconds. And again, here it repeats every 10, 20, every 10 milliseconds, 10, 20, 30, 40, 50. So the frequency is always 100 Hertz. But if you watch 100 Hertz for 50 milliseconds, then it's not the first harmonic anymore. Because in 50 milliseconds, 100 Hertz can be seen 5 times. So in this case, you still have the same frequency, 100 Hertz, but if you see it 5 times, and you see it 5 times because you watch the signal for a longer time, then you will see that it's the 5th harmonic. And that's why now 100 Hertz is here at the position 5 of the spectrum, which corresponds to the 5th harmonic. Because in 50 milliseconds, you see it repeating 5 times. And, of course, twice, the spectrum which was before 200 Hertz, now it will be at 10, at the 10th harmonic, because now everything is multiplied times 5, okay? Fine. This is important because for mathematical reasons, I really don't have time to explain. The spectrum of a digital signal is periodic. If you go to watch the formula of the DFT, or the discrete Fourier transform, you see it why. What does it mean? It means that that's also another difference between the digitized signal and the analog signal. Okay, the spectrum of the digitized signal, once you convert from analog to digital, it's periodic. So if you watch for the higher frequency, it will repeat equal to itself. Okay. So if you increase the sampling frequency, we saw before, it means that you have some extra points here at the tails, which means that you take this periodic repetition of the spectrum far away. What if you decrease the sampling frequency? Well, the condition of the sampling frequency that we described before, that means that the sampling frequency must be larger than twice the maximum frequency of the signal, is the minimum to avoid collision of this spectra. If you have a lower sampling frequency, then the spectra would smash together, and that's mathematically bad. Okay, that's another way you can see this theorem. For the record, there are way more fancy way to describe this this theorem. I just gave you the very simple one. There are very sophisticated way to prove this theorem, okay? Much better than this one, but just to let you understand. Of course, if you have the sampling frequency which is equal to twice the maximum frequency, then you would still collide here at the very tail of the spectrum. So the only way to avoid this spectra to collide is to have sampling frequency which is larger than twice the maximum frequency. So, how many bits do I need? Now, I still have 12 minutes. So it means that I can give just a brief introduction, so I will leave you with a cliffhanger for the next lecture. Now, so far, we talked about frequencies which are concentrated in a single frequency. 100 Hertz, 200 Hertz, 42 Hertz. It means that the signal is there at that frequency. But what happens if you have a continuous, if you have a signal with a continuous spectrum? Which means that you have a signal which contains all frequencies. Not only 100, 200, 300. Not only 1, 2, 3. Not only 10, 15, 17. I don't really understand how you can read the amplitude. So you can read how you can read the amplitude harmonic graph. Oh, okay. It's like this. So your colleague is puzzled because he doesn't understand this graph. So when you take the samples, you take, let's call them S1, S2, S3, S4, S5, and so on. So these are numbers. This belongs to real numbers, okay? Then you apply the DFT and you get, let's call them S1, S2, S3, S4, okay? These are complex numbers. Do it, okay? So in this case, okay, I can write you down the formula just to make it easy. S of k, so the kth harmonic of the spectrum will be, so you have to make the summatory of 1 from 0 to 2n. Then you take all these samples, so Si, so they are real here, okay? So you take real numbers and you multiply times e to minus j. Okay, here there is something to erase. So you have 2 pi. I use j instead of I, or it's just an imaginary number, okay? So we say I divided 2n plus 1, and then the harmonic, k, okay? Okay, if you want the first harmonic, S equal to k, you put 1 k here, and you get I divided 2 plus n, and then you multiply each real number times this complex number, and you get a complex number as an output, okay? So this is a complex number. This is a real number. So basically, you weight this complex number given by the exponential by the amplitude of all these numbers, and you get out a complex number. Each complex number, so if you don't trust me, try to do something with a computer. Each complex number has an amplitude and a phase, okay? So what we do is to plot this graph, to plot these values in some graphs, okay? So here you have the frequency, here you have 1, which means that this is the first harmonic. So here I will plot A1, and actually divided by 2, because then I have minus 1 here. Okay. So the value of this arrow corresponds to half of the amplitude of the first harmonic. So this is for the amplitude. And this is for the phase, okay? So let's say that you have a phase of pi half, and here minus pi half, because it's the opposite. This will be the phase 1, okay? This will be amplitude 1 divided by 2, and this is phase 1. So for each harmonic, you see, I don't know, for the 7th harmonic, you will see an amplitude, and then a phase, which corresponds to these two values, okay? If it's not clear, maybe I will make a short tutorial. Now, let's continue here. What if you have a continuous spectrum? In this case, we always talk about discrete. We always talk about signals which have always some content on a specific frequency. 100 Hz, 21, 42, whatever. But there are, unfortunately, or fortunately sometimes, some signals which have spectra in every frequency. Just think, for instance, to the noise of an amplifier, okay? They have a spectrum which is something like that. It goes down, if it's logarithmic scale, as 1 over the frequency. Then there is a white noise, and you have some noise here at 100 Hz. You have some noise here at 200 Hz. But you have also some noise here at 100.12357.242. Okay? There is no reason why you should find some noise only on one value and not on another, because they are just random processes. Okay? So 100 Hz doesn't have anything special with respect of 101.12357.242. From the physics point of view, there are just two frequencies which are both acceptable when you have some random frequencies, random processes. Okay. We have a problem though. When you digitize a signal, then the space in the spectrum will be only here at discrete value of frequency. First harmonic, second harmonic, third harmonic. You don't have anything in the middle. You don't have the 1.5th harmonic. You have either the one or the second. You have either the second or the third. There's nothing in the middle. You have integer number of harmonics. 7, 8, 9, 10. But that means that when you try to digitize a signal, which is a continuous spectrum and not a discrete spectrum, each line of the harmonics in the spectrum of the digitized signal will not represent one harmonic, as we did so far. It will represent a slice of this continuous spectrum. So this line here at 7 will represent 7 Hertz. It will represent not only the content of the spectrum, the content of the signal at 7 Hertz. It will represent this whole slice here around, well, I'd say something not very technically correct, but forgive me. A slice between 7.5 and 6.5 and 7.5, okay? Now, what happens if you increase the number of harmonics, okay? How do we do that? If you want a new space here between 7 and 8, you have to increase the sampling time, okay? So if you have this larger time you observe the signal, if you remember before, we saw it here, here, then you have new harmonics between the previous one. Here you have 1, 2, and then here you have new harmonics in the middle, okay? New harmonics means that each harmonic will represent a slimmer slice, okay? So it means that the arrows will be smaller because each of them represents a slimmer slice of the cake, where the cake is the spectrum of the signal. So the question is, you have a signal. It has a continuous spectrum. And this and you digitize it. If you digitize it with the frequency resolution of 1 Hertz, which means that between each harmonic, there is a difference of 1 Hz, 7, 8, 9. Between them, there is always 1 Hz. Okay? You have a frequency resolution of 1 Hz. You get these arrows, these amplitudes. If, on the contrary, you have a frequency resolution of 0.5 Hz, like in the second example, you see that the arrows are smaller. But the signal is always the same. So how is it possible that you observe your signal for a longer time and you get something different? That's weird. It's like if the signal is always that, the spectrum should be always the same. I can watch it better with more points, but the value of the points changing because I take more points, that doesn't make much sense, right? So we want a spectrum which has an amplitude, the arrows amplitude, which is the same regardless how many arrows I take, regardless how many harmonics I have. And you can do that by dividing by delta f, the sampling frequency. Actually, to be more precise, you need to take the power in volts square. Now, don't freak out. I know that volt square is not power. Just assume that you have 1 ohm resistance, and then watt correspond to volt square, yes. So if you take, it turns out that if you take the power, so the voltage squared, and you divide it by delta f, then the amplitude of the arrows does not depend anymore by the delta f, because you divide it by delta f, okay? This is called power spectral density, okay? Power spectral density tells you how much there is of density in that slice of frequency. You have a signal, I hope you can see also this part here, and this is the spectrum of the signal, and I watch here how much is the density of the signal in this slice of the spectrum, okay? You have to take the power, so you square, and then divide it by delta f to make it independent on the width, okay? The width is here, delta f, okay? The width of the beam. So regardless the width of the beam that you take, you get always the same value. And now we go back to the point. Why am I explaining all these things to you? Because this is necessary to understand the concept of how many bits to answer to our, this is necessary to answer to our previous question, which was how many bits I need. But now the time is over, if I'm not wrong, and therefore I will give an answer to the next lecture. If you have any question, we are already over time, so just let me know. I have to leave some time. So if you have any question, type it on the Microsoft Teams. Otherwise, we see you tomorrow. We see tomorrow. Okay. No questions? Ah, the assignment that I mentioned. Well, I guess you arrived late, probably. I can explain it to you now, if nobody gets to the room and asking to be here, okay? So if they kick me out, I cannot continue, okay? Or maybe, actually, I think there is the recording. Yeah, we are recording the lecture. So this video will be available later, and I can give you the time, the moment when I gave this assignment, so you can. Or even I think I can write it directly here on Teams, so you can know how to do it. Okay. Okay. Nothing else? Somebody clearly said that is already left. Okay, if there is nothing else. Actually, I have to watch there, not here. If there's nothing else, you can disconnect and enjoy your afternoon, or the lectures you have to follow after me. Okay, bye.